Okay, so welcome for those in the room. Welcome to Rolls-Royce, and welcome to those online as well. So this is not a voice you're probably expecting to hear, because you usually expect to see Mike Bartley, but unfortunately his train was cancelled. So you've got me for a little while anyway. Mike should be here about 10:30, so it'll all start running smoothly about then. But if it's a bit clunky, I apologise, but there you go. I'll just run through Mike's initial slides, but before I do that, a couple of things for people in the room. There's no planned fire drill, so if the fire alarm does go off, there's a fire exit just over there. Just follow me. We congregate out in the front of the building, so no problems at all. The other thing is the restrooms. They are all behind us, just over there. To go out the room, turn right, and then they're in front of you. If they're, for whatever reason, they're being cleaned or something, there's a further set. Just carry on down the building on the left. So, or ask me and I'll show you. Anything else? We've got lunch booked, teas and coffees booked, and all that sort of thing. If you could try and stay in this area, don't go wandering off, because I think last time we had some people here, a large group. There was a few people from supply chain complained because they've got lots of metrics up on the wall that they don't like to necessarily let people see. So yeah, if you just kind of stay in this area, that would be good. Okay, right. Okay, let's get on with this. So so as far as the attendees for today, there is supposed to be 32 people. Now, there's not 32 people in the room yet, so I'm assuming there's a few people going to arrive a bit late. They may have been caught on the same train as Mike. They've got remote registrants of 229, so it's quite a few, and then a total of 181 companies. So quite a good selection of people. So the agenda, which I will try my best to stick to, and I can race through my slides to make it up time, no problem. So first of all, it's me. I'll just give you a bit of an overview of Rolls-Royce, what we're doing, what we've done in the past, what we're doing in the future, and then try and relate it back to FPGAs, because obviously this is an FPGA forum. Then we'll go on to the actual meat of the agenda, which is various talks from experts who are going to tell us about their FPGA developments and verification. Then we have lunch at 1:30. For those that are signed up, there's a tour. I think there's about 10 people signed up, but if you desperately want to be go on that, then let me know. We possibly have a couple more spaces for that. Then we got some refreshments and networking at the end, so it should all wrap up probably about 3 o'clock-ish or something. Okay. And thank you to everybody who's going to speak. There we go. Right. So if I just grab. Right. Okay, right. So ordinarily, Mike would introduce me, but I'm going to have to just introduce myself. So I'm Dave Sanders. I am an associate fellow here at Rolls-Royce. Been working in this business, not necessarily in this building or for Rolls-Royce, but I've been working in the controls business since 2000. So January is my 25th year, which is good because I get an extra 5 days holiday. But thank you. Yes. So all that time I've pretty much been working on FPGAs and ASICs, mainly in the design side, a little bit in the verification. But yeah, so what I'm going to do is just go through a bit of history about Rolls-Royce, what we're doing, and then say a bit what we do on this site, and then how that relates to FPGAs as well, and cover a couple of challenges which I think will hopefully spark some conversations in the breaks, and also I think some things may be answered by the speakers later on as well. So, first of all, Rolls-Royce, 1906 was when it was first became a company. So Charles Rolls and Henry Royce got together in about 1904, and they created a car, or Henry Royce created the car. In 1906, they created Rolls-Royce and launched the Silver Ghost, which was pretty popular. They're the best car in the world, as they say there. So that's then you move on to about 1914. So it's the start of the First World War, and the government actually asked Rolls-Royce to produce an aero engine. So at the time, they were still just making cars. But Rolls-Royce developed the aero engine, which was the Eagle, and that was the first aero engine produced by Rolls-Royce that actually went on to power the first transatlantic flight as well. So those were used in the First World War on various bombers, etc. We move on. There's lots of further development in aero engines. One being the Merlin, which is actually the last engine that Henry Royce designed. He died in 1933. The Merlin was first flight flew in 1935. So by 1940, during the Battle of Britain, by the Battle of Britain, the Rolls-Royce Merlin engines were used in the Hurricane and the Spitfire. And there's a picture of a Spitfire that's actually taken from one of the air shows about a few weeks ago. So there's a few of them still flying around. Pretty spectacular planes. So in 1944, morning everybody. 1944, Second World War, obviously continuing, and Rolls-Royce have started to develop the first gas turbine. This was pioneered by Sir Frank Whittle, and he's largely credited with inventing the jet engine. So they didn't go into service in the war, but they started the development of it. Then we move on to 1953. So Rolls-Royce had produced all these aero engines, mainly for the military. So in 1953, they actually put it onto a civil aviation market. The Dart turboprop aero engine was fitted, as you can see, 4 engines on the Vickers Viscount medium range airliner. So that actually was one of the reasons why that particular engine was kind of drove the acceptance of gas turbines within the airline industry. Then we move on to a bit of a dark period of Rolls-Royce, 1971. We were developing the RB211, which is the first 3-spool engine. There's a picture of it there. And the development costs spiraled out of control. The performance wasn't where it needed to be. The weight was too high, and it was too expensive. And that meant that the company pretty much went into bankruptcy, and the government actually took ownership and nationalised Rolls-Royce. And then pretty much at the same sort of time, a couple of years after, the Rolls-Royce Motor Company actually split off from the aero engine. So we don't make cars anymore. That's BMW make cars. So there's about 16 years of state ownership for Rolls-Royce. 1987 went back into the private sector, which is a good thing. And since then, there's been lots of mergers and acquisitions. So effectively, we're one of the only British companies capable of delivering power on air, sea, and land. So a lot of these things I talk about, and the next slide as well, is focused very much on the aerospace. That's because this building generally services the aerospace industry, but there are other areas as well for Rolls-Royce. So moving on to 2005. So my involvement is a few years earlier than this. I wasn't involved on this particular engine though. I was aware about it when I first started. This is the V-22 Osprey aircraft, a very iconic aircraft for the US Marine Corps, and it's a tilt rotor. They're very exciting plane, and yeah, I think very successful as well. So the sort of takeoff ability, it's a tilt rotor, so take off like a helicopter, then tilts the rotors and then can fly off the plane. So 2007, we move into quite a period of lots of engines being created, civil engines for different applications. First one being 2007 Trent 900, which is from the A380, which you'll hopefully aware this the very large super jumbo with the double deckers and the bars on the top of the plane and things like that. So you can see the size of the engine compared to a person; they are absolutely huge, and that's 4 engines per aircraft as well, which is unusual. So 2011, something slightly different, not quite aerospace. We also had awarded a a contract for the propulsion system for the next generation nuclear powered subs. That's kind of still ongoing at the moment. Yeah, that was a very large bit of business for us, and I'll come on to a bit more of that later. On the same year, we also had developed the Trent 1000, and it became the first engine to go on the 787 Dreamliner. So that was the first flight. So that was developed for many years, and I was involved in that one, not on the actual engine, but in the controls bit of it. Then we move on to 2015, A350, which is the Airbus A350, and that went into service exclusively with Rolls-Royce Trent engines, and that's a very successful program of work, to the point where it was a few years ago, somebody made the comment that if we just carved off the XWB is part of the business, it would be a FTSE 100 company on its own, just with that plane. That's how many engines we sold on that. So it's very, very good. 2017, Trent 1010, so it's an upgrade of the previous Trent 1000 that entered into service, and also another variant of the A350. So all of these are different engines or variations on the engines. There's lots and lots of engines occurring in a very short space of time. And to top that off as well, there's the Trent 7000, which is a re-engineering of the A330, so the A330 Neo, that entered into service as well. So you can see there's lots and lots of development engineering going on in those periods, that period of time for Rolls-Royce. And now we're in the situation where it's moving from an engineering into more of a service company. So slightly shifting gears a little bit. In 2021, there was a bit more of quite a lot of a push from Rolls-Royce for net zero. And part of that is for increase our interest in electric planes. So Spirit of Innovation, which is the name of the plane, is an all-electric plane, very, very light, and it has the world record for the fastest all-electric vehicle at 345 miles an hour. So that's something a little bit different for Rolls-Royce, so we usually just burn hydrocarbons. And then finally, on this slide, there's in 2023 a big milestone as far as sustainable aviation. We're using the Trent 1000 engine, which powers the 787 Dreamliner, has had their transatlantic flights using 100% sustainable aviation fuel, or SAF, to power it. That's a huge deal. At the moment, sustainable aviation fuel can't be produced in big enough volume, but at least we proved that the engines themselves, they can run at on this fuel that potentially is sustainable. We've also at the same time tested all of our engines in production and checked they all work with SAF. So that bodes well for the future. Okay, so the last big milestone that we've done as far as development is the UltraFan. So all of those previous engines were all Trent based engines on that last slide, pretty much. This is the next generation, called the UltraFan. It's the largest fan diameter in the world, but it was done that way so then we know, and then we're going to scale it so it can go smaller as well. Obviously 100% running on sustainable aviation fuel. There's lots and lots of new technology in that engine, huge amounts of development and lots of money put into it. Its target is to be 25% more efficient, and that makes a lot. That can coupled with the SAF means that we're on the journey towards sustainable aviation. So as far as the future is concerned, there is lots of other things as well. So I'll just quickly run through these. Then I'll promise I will talk about FPGAs as well. So first of all, Tempest, it's a fighter jet next generation fighter jet. We are involved in the propulsion system on that. I can't say much more about that though, for obvious reasons. Moving on, small modular reactors. You may have heard in the news, you may not. I don't know. Rolls-Royce have won their first contract for SMRs in Czechia. So that's a fleet of SMRs, and I think there's Sweden and somewhere else as well. We are pretty close to getting those deals as well. So that is a brand new part of the business. It's taking our nuclear design, our capability that we've got from the subs, and applying it to a small modular reactor, which creates 500 megawatts of power. Other big opportunities as far as the US arm are concerned is the B-52 re-engineering. So that to keep that going for many more years, and that's worth a lot of money, as you can imagine. Actually, on the same thing on the American, we flip down to the Flora, which is the bottom left picture. That is the future long-range assault aircraft. So it's the Black Hawk replacement. So that has been developed or going to be developed over the coming few years as well. Again, through our US colleagues. Moving up to the to AUKUS. That's the Australian, UK, and US sort of collaboration, where we signed an agreement to provide submarines to Australia, but also develop some new ones as well. So that's a very long-term project. And then the two in the middle there as well, got energy storage and microgrids. So we have some an arm of our business in Norway. That's power systems, and the power systems are looking at various things to do with decarbonisation of our energy production, and things such as microgrids and energy storage is front and centre of that. They also do a lot of other things that I don't have any information about. So, and then finally, the one that's a bit interesting as far as a bit off the wall is taking our technology that we developed in the submarines and shrinking it even further to create what's called a micro reactor. And those micro reactors can then be used. The idea being they're used in several different applications, one being space, so actually powering spacecraft, but also powering bases on the moon, a permanent base on the moon, which is quite exciting. But that same technology could also be put in a container and used for remote terrestrial power. So things like remote bases, or if there's a disaster, you could drop one of these containers and provides power, emergency power to places, or industrial, etc. So lots of things that we're going to be doing, and think of all these as well. They all require control systems, which is where this building comes in. So what we do here, well, not just what we do. We do electronic controls. We also do hydromechanical part of it, which is the other half of this building. But the bit I work in is the electronic controls. So you can see picture of the engine there, and that's the EEC, the electronic engine controller, that's mounted directly on the side. So that means that we are very much in a very harsh environment. By harsh environment, I mean temperature, so it's minus 55 degrees up to 125 degrees centigrade. It's atmospheric radiation. It's got to be susceptible to atmospheric radiation, so that's upsets that happen due to cosmic radiation from the sun, etc., which is far more more prevalent when you're up at 60,000 feet. It has to be there for a long service life, so typically 100,000 hours, which is 8 hours a day, 8 hours a day for 20 years. That's the standard operating life. And because of that, we have to have obsolescence management, so we can't just go for the latest and greatest FPGAs or processors. There are things we need to do to make sure that we don't end up in a hole. And obviously, because it's a very safety critical area, we have to comply with the various regulations, DO254 being the FPGA ASIC regulation that we comply to. So as far as the FPGA, what do we use the FPGAs in boxes such as this shown on the picture? Well, there's multiple things that can be boiled down into, first of all, providing an interface between analog inputs and outputs, and the microprocessor that we have on our inside. It also can be used for some engine health monitoring and some areas of communications as well. So what are we doing at the moment as far as future developments? We are looking at a high integrity switch. So if you look at the ultrafan that I showed a picture of earlier, it has a huge amount of I/O on that ultrafan, and that is therefore the size of the box gets so large you can't strap it to the side of the engine anymore. You end up having to have multiple boxes. And if you have multiple boxes, you've got to have a way of talking, and so we are developing a high integrity switch which uses Iron 664, and actually Cognietics helped us with that as well. So, and they're in the room, so if you want to know anything about the switch, you can ask them. Then also we also design our own microprocessor. So we don't use ARM, we don't use Intel, we don't use any of those. We actually design our own. And the next generation one, which is called the R7, that is currently being developed. I'm the lead of that project. And so if you want to ask anything about that, I'm happy to talk for hours on that one. That's the picture there's the last generation. That's a GR6 processor. So motor control, that's another area of FPGA development. This is, again, a shift more towards the more electric engines to try and make them more sustainable. But equally, there's benefits there commercially as well. So there are things such as the starter generator, electrical starter generator that we can add to engines. That replaces a whole bunch of line replaceable units that are far heavier. So we actually gain for, we lose weight off the engine, which means the engine is more efficient as well. So that's a big area of FPGA design. So current status of the verification. So we've been doing FPGAs in this business since about the mid 1990s. Started off with VHDL. Well, we still do VHDL for design. Actually started off with schematic capture, but that's so VHDL design. And we did do VHDL test benches up until about 2012. When we adopted System Verilog and UVM. That is what we do now as a policy. We just use System Verilog and UVM test benches for everything, apart from quick and dirty sort of design-led test benches. Then a more recent addition is our emulator, the Siemens Veloci emulator, which we bought a few years ago, and we're starting to use in anger. And that is basically just allowing us to speed up our regression testing. So, current challenges in recruitment. Current challenges in verification. The main one, I think everybody in this room will probably agree with this, is recruitment and retention. We find it very, very, very difficult to find good caliber people at a price we're willing to pay. And also when we get them, and holding on to them as well. So the market is very competitive for those people. So we're looking at effectively trying to grow our own. So looking at graduates more. Unfortunately, for the last few years, that's kind of since COVID and various restructurings, our graduates program has kind of dropped off a little bit. And we're certainly seeing that now, the ramifications of that. So I'm hoping to get that restarted, but equally get it restarted in more of an FPGA and ASIC focus as well. At the moment, so previously we would get 10 students in who are electronics. I actually want to try and get some targeted 1 or 2 a year at least into ASIC FPGAs. And hopefully if we get 1 or 2 or 3 every year, then 1 or 2 will stay around for a reasonable amount of time whilst they become useful. Because the other point is learning curve is really, really steep, and I'm sure again I'm not saying anything that's profound there. Especially UVM and System Verilog, it is very difficult. But then if you layer on top of that DO254 and the requirements that we have, it makes it very difficult to get good quality work out of people quickly. They'll end up having to grow them over many years, and then by the time they've got all those skills, they then look up and go, "Oh, I can go and double my wage over the road or whatever." So it's quite tricky. But that is all I had to say. So I'm done now. So any questions from the room at all? No? Good. Okay. Hopefully that was all right. Okay. So any questions from anybody online at all?
David, there's one question I have just posted on the chat box.
I'm not seeing anything.
Okay. Okay, I will just okay. It says, what is the typical selection criteria between FPGAs and DSPs? Why FPGAs have been selected over DSPs for the specific applications? That is the question.
Okay. Okay. So okay. So DSPs are it's mainly down to obsolescence, I would say. So you design an FPGA, the code that you create is portable. So you could in theory port it across to a different FPGA. DSPs, I think, are and there are also FPGAs out there that are have got long life cycles. Whereas DSPs are far more prone, like processors, then far more prone to getting obsolete. So obsolescence is a massive issue for us, which is the reason why we create our own processor as well. It's exactly the same reason. So any function that was required, any sort of computation, we would put it on our own processor before putting it on a DSP. We don't use DSPs at all. The only slight difference to that is if it's in a lower criticality unit, we may consider a DSP, but even then we haven't. What we've ended up doing instead is using a more kind of a system on chip FPGAs like Xilinx for lower criticality. So hopefully that answers your question.
Yes. Thank you, David.
Okay.
Yeah.
So hold on.
20, 25 years.
Yes.
Going back 20, 30 years. Is that still the case?
Yeah. So typically it's 20 years, but there are cases like, for instance, on the Trent 700 engine that was first went into service in the mid 1990s, early to mid 1990s, and it's still going in production now. And we've still got orders that will go in production until 2040. That's production. So you've got, yeah. So then you've got 20 years on top of that. So 2060 by the time we've retired all the Trent 700, and that's with current orders. Yeah. So yeah. So there's on the Trent 700, it is a what we call a toaster rack unit. So you've got a main motherboard and lots of small cards. One of those is the computer card, which has been replaced 3 times already. So yeah, and that was the last one we replaced. I think it's 2018. So I'm hoping that's the last time I have to do it. Okay, thanks for that.
Do you use discrete memory, or do you implement memory in the FPGA?
So yeah, we do still use it as discrete memory, although we've recognised that's the thing that goes obsolete as well. So certainly with the GR6, we actually had it as a multi-chip module, and the memories were on board, and we did actually design our own RAM as well. But yeah, because that was just easier that way. But it's there's you either design it yourself or you have a good partnership with somebody who're going to guarantee this production, or you have a die banking facility, and we kind of do all of those. Yeah. Okay. Right. Yes. Thank you.